Hi class, this is Sir Alex Vasco and welcome to General Physics 2. Today we are going to discuss our lesson 9 for today, which is all about equipotential lines and electric field. Previously in lesson 8, what we've discussed is basically electric potential and electric potential energy. Those are two very different things, so I hope you guys don't get confused between the two. Electric potential energy is a potential energy, much like gravitational potential energy. When you place an object above a surface, we know that that object will fall down as soon as we release that object. It's because when we raise something above the ground, we are adding some sort of potential energy onto that object. And once we release that, the potential energy is being used and converted to kinetic energy. Similarly, for charges, when we place charges along a electric field, that charge began to have an electric potential energy, and the amount of work done for that charge to move against an electric field, that is the electric potential energy. Electric potential, however, is electric potential energy per unit charge. So it is basically the units of joules per coulomb. So that is the difference between the two. Again, electric potential energy is a potential energy. Once you place a charge in an electric field, that charge can move, and the work done, or when it moved, there is work done, because work done is basically force times distance. That charge, when you placed it in an electric field, it experiences a force, and when it moves because of the force, there is work done, and the work for that charge necessary to move against the electric field is what we call the electric potential energy. Hence, we have the equation W is equals to negative U. Electric potential is the electric potential energy per coulomb charge. So that's where you got your negative U, or your U divided by Q. Okay, so I hope you guys made the distinction between the two. Now what we are going to do is to identify electric potential in terms of electric potential or equipotential lines. Much like electric field, when we draw electric field, we tend to draw it we tend to draw electric field in some sort of lines. However, for electric potential or equipotential lines, we draw it in some sort of concentric circles, and that's what we are going to do today. Identify these two things, and then kind of like find the relationship between the two, because we can actually find the electric field using equipotential line. But before that, let's go understand our goal. Why do we want to do this? Because what we want to do is for us to be able to infer the direction and the strength of electric field vector, basically meaning we want to find the direction and the magnitude of the electric field vector, or the nature of the electric field sources and electrostatic potential surfaces if we have the equipotential lines. That's what we want to do. Identify the equipotential lines and then find the following: electric field vector, the direction and the magnitude, the nature of the electric field sources, is it positive, is it negative, and the electrostatic potential surface. So understand that electric potential on multiple charges. That's something that we have to understand first. If you have several charges, the potential at a point, again, potential here, we are talking about electric potential. It's the amount of electric potential energy per coulomb or per charge. The potential at a point due to these charges is simply the algebraic sum of the potential due to each charges. So this is the total potential or electric potential. In order for you to find the total electric potential when you have multiple of charges, you just have to find the individual electric potential of each of those charges, add them all up, and that's how you get the total electric potential. So similar something like this, you have a picture right this where you have your Q1, Q2, and Q3 at varying distance to P. Q1 at the distance R1 to P, Q2 at the distance R2 to P, and Q3 at the distance R3 to P. And from the previous discussion in lesson 8, electric potential can be measured using this equation, KQ divided by R. So that means is that the electric potential of a charge, at a certain point within a certain distance is basically the Coulomb's constant multiplied the charge of that the charge of your Q divided by the distance to the point. That is the electric potential. And if we have multiple of these, we just have to find each individual electric potential. That's why we have our Q1 and R1, Q2 and R2, Q3 and R3, and then add them all up to get the electric potential total because of multiple charges. Now let's talk about equipotential lines. Electric potentials can be pictorially depicted via equipotential lines. So again, much like electric field, we can actually draw these equipotential. So meaning, if we go back to this, so if I have my Q1, I have my electric potential here. And if I keep getting the electric potential for these values, for this Q, so if I want to find the electric potential here, electric potential here, electric potential here for Q1, eventually what I would get is actually a concentric circle that we can draw this way. So let's say I have my positive charge right here and it has an electric field. The equipotential line is something like this. Equipotential lines, from the word itself, equi meaning equal, potential, so the potential of that object at that certain distance, and then we can talk about it as line, but if you look at them, they're kind of like circle, right? But in reality, they're actually 3D space. Much like the electric field is not a 2D space. This electric field is pointing in every single direction, encompassing this positive charge. Much like this electric field, the equipotential line is also a 3D space. You can think of them as a circle or as a sphere encapsulating the positive charge. That's why equipotential lines can also be called equipotential surfaces, because they're in a 3D space. But what does that mean? Is from the name itself, equipotential lines, is that if I have these points right here, meaning I want to find the potential of this charge at point A, and then the potential of this charge at point B, and the potential of this charge at point C. Something that you have to realize is that A and B, the potential between A and B is actually the same. That's why we have equipotential, equal potential. The reason for that is because they fall in the same, they fall in the same surface, or they fall in the same line. The reason for that, we will explain later, is because of their distance r. So equipotential is potential is actually dictated by the distance. Equipotential lines are usually drawn in, but before we talk about that, just understand that equipotential lines are drawn as concentric circles around your charge. The potential for each line at a distance r is constant. So again, if we talk about this, what is the potential difference if we move the test charge from point A to point B? So potential difference is the difference between the potential from moving one object to the other, like from one place to the other place. Usually what that means is v final position. We also discussed this already in lesson 8, and v initial position. So if you think about this, so what is the potential difference if we move test charge from point A? So I have, for example, a test charge here. I place a positive charge right here at point A, and what if I move it to point B? Similarly, what if I move my test charge, which is at point B now, to point C? So let's see what will happen. The electric potential at distance r is constant because this is the equation that we just talked about earlier and previously. The potential is equals to Coulomb's case constant multiplied by the q divided by the distance. The change in the electric potential if I move it from A to B should be 0. The reason for that is because the electric potential at this point in A and the electric potential at this point in B, VA is equals to VB. The reason for that is because the distance from the charge to your A and the distance from charge to your B is actually equal. So if this is equal, and your Q is not changing because this is your Q, and your K is constant, what happens is that VA is just VB. So if I move my charge from A and I move to B, the potential is the same. So if I find the difference between the two, that's just basically VB minus VA, because this is my final destination, my initial destination, it will just be 0. So the change in the electric potential in moving the test charge from A to B is 0 because there is no work done. So the work done, work is equals to negative Q. This is basically U, right? This is potential right here. And that is negative Q multiplied by the potential difference. That's why you have your delta V here. Delta V is equals to VB minus VA. And since VB minus VA is equals to 0, that's why we have it here, 0, then the whole work is 0. There is no work done from moving my charge from A to B. Now let's talk about if we move B to C. Is there work done? The answer is simply yes. The reason for that is because the distance between the charge to the position B or to the point B is R, and if I measure that from the charge to C, the distance is not equal. Hence, what happens is that the potential actually becomes lower because the distance become greater. There is a inverse relationship between your V and your R. V is equals to 1R. You can think of it this way: as this increases, this decreases. Similarly, if I decrease this, this also increases. If we go back to the situation here, the distance from B to C, the distance to C is much higher. So moving it to a distance C now has higher R. Hence, the potential should be lower. Okay, so that's basically what is happening. So if I move again from A to B, there's no work done. But if I move from B to C, there is work done. And again, this is a 3D space. So note, the equipotential lines are used, although used in 2D representation, they're actually in 3D. So they are field, they are surface, they are sphere surrounding the charge. Another thing, equipotential lines or surfaces are not always circular. If you look at this right here, they can mix together. much like the electric field, they can bend. The electric but equipotential lines can actually also bend. In fact, that's why they curve. So there could exist the various shapes depending on the number of charges present at the value of their charge. Now let's talk about the relationship between your equipotential line and your electric field. First, electric field lines will always be perpendicular to the equipotential lines whenever they intersect or meet. Another, electric field is stronger where equipotential lines are closer together. So the equipotential lines are actually much closer the nearer they are to the charge. And lastly, electric field lines always point from high potential to low potential. What do we mean by that? If we look at these two equations or these two diagrams right here, this is my charge right here, and this is my electric field lines, right? This purple arrow here, and this green right here are my equipotential lines. What you would notice is that if you look at a very small object and or if you look at an object and you zoom in these intersections right here, what you would always notice is that the electric field will always lie perpendicular to your electric equipotential line. Because interestingly, if you actually have, for example, a curve and then you zoom in really close to that curve, what you would see is actually just a straight line. So having said that, again, so if you have a curve and then you zoom in on that curve, what you will end up seeing is just a straight line. That's why the earth, if you look at the horizon of the earth, it is very straight. The reason for that is because we're basically so small, we are zooming in onto the curve of the earth, and once you zoom in, it looks like a flat line. So when an electric field intersects that curve, what you ended up seeing is just a 90-degree angle. So the electric field will always be perpendicular to the equipotential line. Another thing, the electric field will always be stronger where the equipotential lines are much closer. So if I keep drawing my equipotential lines, what you would notice is that these equipotential lines will get closer and closer, and the electric field are actually much stronger at this point. And lastly, electric field will always be pointing from higher equipotential or higher potential to lower potential, even if it is negative or positive. The reason for that is if this is positive, the voltage, or basically the potential, actually gets bigger the closer you are to the positive charge. And since this is positive charge, the electric field will always be radially outward. So the direction of the arrow for the electric field will always be going outward. And hence, if you are going to look at each of those individual equipotential line, what you notice is that it's pointing from higher potential to lower potential. The same is true for the negative charge. The negative charge, as you go closer, the negative charge, the equipotential line for this negative charge actually gets lower and lower. So you can see here, you have -10, -20, which is much lower, and -30, which is much lower. And the electric field for a negative charge will always going to be radially inward. This is your E, and it's radially inward because this is negative. And if you look at the relationship again, you would notice that the electric field always points from lower potential to higher potential. So having looked at these various relationship between the two, we can actually come up with an equation. So the equipotential lines, using the equipotential lines, we can infer the magnitude and direction of the electric field and the nature of its source, and vice versa, using this equation, wherein you have the magnitude of your electric field is equals to the electric potential difference, meaning the difference of the potential between these two areas. So if I measure the potential of this difference, this is basically -20 volts minus -30 volts. So what that means is negative 20 plus 30, that's negative 10 volts. And what you would notice is that the potential difference between these two is negative 10 volts or positive 10 volts. And if you look at this as well, the potential difference between the two is also positive 10 volts. So using this equation, you have your D. The D here is the distance between those equipotential, not the distance to your charge particle. So where E is the magnitude of the charge, negative or delta V is the change in the electric potential, and D is the displacement of the electric field. So now let's put those into practice and let's answer this sample problem. Let's move on here.